everyone, and welcome to this tutorial on futures and asynchronous programming. My name is Dimitra, and today we will explore HPX capabilities in asynchronous programming, detailing how futures and async functionalities can be leveraged to write efficient, non-blocking code. We will use real-world examples to demonstrate these concepts, providing users with practical use cases. For this tutorial, you need to have your HPX installation complete and know how to compile and run an HPX application. For this, we have a different tutorial with a Hello World example, which I will link here. Let's begin with the first example. Our goal is to create a vector of numbers, apply an asynchronous computation to each element, and then print the results once our computations are complete. This is a great way to understand how to use futures and asynchronous programming in HPX. So in HPX, we use futures to keep track of asynchronous tasks. But what is a future? A future is an object that acts as a placeholder for the result of an asynchronous computation. So when you launch a task in HPX using HPX async, for example, or similar functions, it immediately returns a future, which can be used later to check if the task is done, retrieve the result once it's ready, or synchronize multiple tasks. So let's start with the code. We first create a vector data with 10 elements, or initialize to 1. We also prepare an empty results vector of the same size to store the output. We use a vector of future to store the asynchronous tasks we launch. This will allow us to keep track of them and wait for all to finish later. HPX future void represents a task that doesn't return a value, but performs a side effect like modifying results. We loop through each element of data, and for each one, we launch an asynchronous task using HPX async. This launches a lightweight asynchronous task to perform the operation. The task is defined by a lambda function. The lambda function captures I by value and the rest of the variables, data, and results by reference. Each task calculates data I times 2 and stores it in results I. The future from each task is stored in the futures vector. Now we need somehow to synchronize our tasks. We do when all futures wait. This waits until all the futures in the futures vector are ready. That means when all tasks have completed. Now we can print the results. Without this line, the program might try to print the results array before all tasks have finished executing. So another way to execute a piece of code after all tasks are synchronized is using then and adding your code there. So HPX when all futures returns a future that becomes ready when all the individual futures are done, and then adds a continuation, so a function that runs after all the tasks are finished. In this continuation, we print both the original data and the computed results. And finally, we block the main thread until all tasks and the printing are completed. So, to sum up how futures work in HPX, we create an asynchronous task. So we start a computation using HPX async, and we get back a future. Then the task runs in the background, possibly on another thread. And if needed, we can wait for the result using get or wait. We have already compiled the code, so let's go ahead and run it. As we can see, the initial vector contains 10 elements, all set to 1. After running the code, the result vector contains 10 elements as well, but all set to 2. This matches our expectations, as we multiplied each element of the initial vector by 2. Let's see now a more interesting example, the game of life. Imagine you have a grid made of square cells, like a chessboard, but much larger. Each square can be either alive or dead. The game progresses in steps or generations, and at each step, the cells follow a set of simple rules to determine whether they will stay alive, die, or come to life. So let's see the rules of the game. Each cell looks at its 8 neighbors, left, right, top, bottom, and diagonals, and decides what to do based on these rules. A live cell with 2 or 3 neighbors stays alive. If too few, it dies of loneliness. If too many, it dies from overcrowding. A dead cell with exactly 3 neighbors becomes alive, as if it were born from the surrounding cells. And in all other cases, the cell stays dead or dies. But why is this interesting, and why would one use HPX? These simple rules create complex patterns, making it a fascinating problem for all parallel execution. Since each cell updates independently, we can compute updates asynchronously using HPX. So let's have a look at the code. To implement the game of life, we need to structure the implementation so that each cell update happens asynchronously using HPX futures. So the main idea is to define the grid, a two-dimensional grid representing the state of each cell, apply the rules asynchronously, so each cell's next state is computed in parallel, and use futures for synchronization. Ensure all updates complete before proceeding to the next generation. But how this works? So first we include the necessary headers and we define constants for our grid size and the number of simulation steps. The grid is a 2D vector where 1 represents a live cell and 0 a dead cell. We first need to count the alive neighbors for each cell to determine its next state. We create a function called countAliveNeighbors, which returns an integer with how many alive neighbors a given cell has. The function takes the grid as an argument, which is a 2D vector, so we have std vector of integers, and it takes this by reference so that we ensure that it doesn't copy the grid, and this is only used for reading. It also takes the coordinates of the cell for which we are counting the alive neighbors. X is the row and Y is the column. Now let's use an illustration to understand better how we count the alive neighbors. So X and Y are the coordinates of the current cell, and we will use an offset, let's say dx and dy, to represent the direction relative to the current cell xy. So for example, dx determines the row offset and dy determines the column offset. So the top left neighbor of xy has position -1, -1, while the top neighbor has -1, 0, etc. Now this illustration maps to the following dx and dy arrays. So this defines the relative row positions of the 8 neighboring cells around the current cell. These values correspond to the directions top left, top, top right, left, right, bottom left, bottom, and bottom right. We do the same for the relative column positions of the 8 neighboring cells. So we have this array. These values correspond to the same directions as dx, but for the columns. And we also need a variable to store the number of live neighbors. So int count initialized to 0. Then we iterate over the 8 neighbors and we calculate the neighbor coordinates. So we do. For each neighbor, we calculate its coordinates by adding the offset from the dx and dy arrays to the current cell's coordinates x and y. And x represents the row of the neighbor, and y represents the column of the neighbor. So let's see now if the neighbor coordinates we calculated are valid. That means if they lie within the grid's bounds. So we have to check if both coordinates are larger than 0 and smaller than the grid size. If the neighbor is valid, we check if that cell is alive. So we add grid and x and y to the count, and if it's alive, so if it's 1, We add 1 to the count variable, otherwise 0 is added. We return the count variable, which is used to decide the next state of the current cell in the game of life. So let's see now the function which we will use to update the grid asynchronously. We define a function named updateGrid that takes the current game grid as input and returns the updated version of the grid after applying the game of life rules. We create a copy of the input grid called newGrid. This is the grid we will modify to hold the next generation state, and we use a copy to ensure that all updates are based on the original current state and do not interfere with each other. We declare a vector of HPX future void. This will hold all the asynchronous tasks that we will launch, one for each cell in the grid. Then we iterate through each cell in the grid using nested loops. So the outer loop goes over each row X and the inner loop goes over each column Y. For each cell, we create an asynchronous task using HPX async. We capture X and Y by values so that each task operates on its own coordinates, and we capture everything else by reference. This ensures each task reads from the correct position in the grid. Inside the task, we call our helper function countAlive neighbors to find out how many alive neighbors the current cell xy has. And we save that to an int variable. Now we apply the first rule of the game of life. If the current cell is alive, so if the grid value is 1, it will stay alive only if it has 2 or 3 alive neighbors. So the new grid value will be 1 only if the alive neighbors are 2 or 3. Otherwise it dies, so we set it to 0. If the cell is dead, it becomes alive only if it has exactly 3 alive neighbors. So the new grid value will be 1 only if the alive neighbors are 3. This models reproduction. So we close the lambda and we push the task as a future into the futures vector. This future will complete when the cell has been updated. After launching all the asynchronous tasks, we wait for all of them to complete using HPX when all futures wait. This ensures the next step of the simulation won't begin until all cells have been updated. Finally, we return the updated grid that reflects the new generation of the game of life. We also add a function to print the grid in a readable format. And now let's have a look at the main function, which initializes the grid, runs the simulation, and prints the output at each step. So here we initialize the grid, which is a 2D vector with dimensions grid size by grid size. Each element in the grid will represent a cell where 1 indicates a live cell and 0 a dead cell. We use these lines to set up the random number generations. So we use a std random device to generate a random seed. And then we use a Mersenne twister random number generator initialized with a random seed. And finally, we define a distribution that generates either 0 or 1 randomly. Then we iterate through every cell in the grid and randomly set each cell to either 0 or 1 based on the random numbers generated by this gen. We then enter a loop to run the simulation for a defined number of steps. Each step corresponds to 1 generation in the game of life. We print the current step number, and we call the print grid function to display the current state of the grid on the console. And next, we update the grid by calling the updateGrid function. This function computes the new state of the grid based on the current state, applying the game of life rules asynchronously. Okay, now if I run the code, you'll see the grid being printed at each step of the simulation. The grid evolves as the game of life rules are applied, with cells becoming alive or dead based on the state of their neighbors. You'll notice the grid changes over each step, and depending on the initial random configuration, some interesting patterns may emerge as the simulation progresses. This example is a great fit for HPX because the game of life is inherently parallelizable. Each cell's update is independent of others, making it an ideal candidate for asynchronous execution. By using HPX async and HPX when all, we can scale the computation seamlessly, demonstrating the power of parallel computing with minimal complexity. Thanks for watching. Happy coding, everybody.